So before I actually start, I'm going to pre-start. I have this remote control car. And about a year ago, I bought a piece of hardware, a radio, that I could connect via USB to my computer. And I figured out I could, because I'm a JavaScript developer, so I could use JavaScript to talk to the radio, obviously, because why not reinvent the wheel? And this radio is super cool because it can not only receive radio waves, but it can send radio waves. And you can program that in software. So I was like, let's see if I can remote control a car using JavaScript. So let's see if, can we get like that camera up there on the screen instead of my? No. No? No. OK. So now I'm pressing forward here, and the car is kind of moving. I don't know if you can see that. Pressing backward. Is there no way to get that camera up on the? Well, none whatsoever. It's OK. You get the point. So I can use my computer here to control the car. Very simple. That's not what I'm going to show you today, so it's not super important. And when I built this a year ago, so one thing is that you can basically emulate the normal remote control you get with a toy car. But the cool thing is then you can like program in maneuvers so that you can automate like certain things. So me and my friend Matthias, we built like a 180 turn where we sort of go forward for a little bit, then block the wheels and turn right to the car. The car kind of slides out, and then put it in reverse and go backwards. So that's kind of how this looks. This is all automated using Node.js with a little bit of slowing down. You can see he's really happy. So software, right? OK. So who am I? My name is Thomas Watson. I do a lot of open source software on GitHub. You can find me there. I'm a Node.js engineer at Elastic. And I tweet on Twitter. So yeah. So the title of my talk is Building a Radio Data Network with Node.js. So I got this about a year ago, and I played around with it. And then I was thinking, OK, wouldn't it be really, really cool if basically, because I'm a JavaScript developer, if I could like re-implementing Wi-Fi in software, right? So if I have two of these, I could make them talk to each other. And we could like just stream data over the radio waves. So that was the goal of me making this talk. And this talk is basically me kind of taking you down the path of what I had to learn to do this. So the concept or the field that I'm working in here is called software-defined radio. And it kind of makes sense if you think about it. This is a radio, and we control it using software. A lot of the normal stuff that's in a radio, like a lot of the hardware stuff that's normally inside a radio, have been taken out. And you basically get raw access to the voltages on the antenna, either setting those voltages, so basically sending radio waves, or receiving those voltages. So basically, there's a little bit of filters and amplifiers in there, but other than that, you basically via the USB you get like the raw radio packets. And software-defined radio is nothing new. So at this company, Edis Research is probably one of the most famous for doing software-defined radios. But it's super, super expensive. You have to be like doing something in a lab where this makes sense. This starts at $5,000 and upwards. But then something happened. This guy here, you can buy it today on Amazon. It's basically a USB TV dongle that you can watch TV on your computer and listen to FM radio. It's very cheap. It's like $10 to $20. But the cool thing is that it contains this Realtek chip that is super hackable. And somebody found out that they could actually access the chip directly, and then it actually supported a range from 24 megahertz to 1.7 gigahertz. So with this, you can basically listen to airplane traffic, you can listen to a lot of other interesting things, and do it all in software. So that's kind of how it all started. Then a little bit later, this guy came along, and that's the piece of hardware I have here, because this can also transmit. It's a DARPA-funded project. It's open source hardware, and it, compared to the first one I've shown you, it's pretty affordable, about $300. So to do this, I needed to learn radio. As I said, I'm a software developer, so radio, hardware, all that stuff was pretty new to me. So I needed to figure out what radio actually is. And this is the most basic form of a radio wave, or any kind of wave actually. It's a sine wave. It's the most basic form of wave you can have. And what you can do with a wave is that you can modify its frequency, so the distance between the peaks and the valleys of the wave, if they get longer apart, you have a lower frequency. If they get closer together, you have a higher frequency. You can also change the amplitude, so basically how much voltage you put out on the antenna, you get a higher amplitude, lower voltage. And when I said this is basically the fundamental wave, it's true, because you can, from that wave, you can generate any other kind of wave. So if you take the wave that goes in through this microphone, it's turned into electricity as I speak. And of course, that wave doesn't look like a nice sine wave, but it is composed of basically a lot of sine waves. And computers, they're pretty good at working with sine waves. So basically, all we have to figure out is really how to manipulate sine waves in software. Then we can generate any kind of wave. So once we've learned that, the next thing we want to figure out is we need to do something called modulation. And modulation, what is that? Wikipedia have this very boring, long thing about what modulation is, which I'm not going to bother you too much with. But basically, it's taking some information and encoding it onto something else. In this case, we encode the information onto a waveform. But this is not something we've only done with radio waves. You could say we kind of have done this forever. We're taking and modulating the smoke with our message. So, and then we get smoke signals, which is basically the most early form of modulation, if you stretch your imagination a little bit. But the actual real modulation came with the invention of the telegraph. And the telegraph is a circuit which is either open or closed. So either there is power or there's no power. It's a very, very simple form of modulation. Either there is something or there is not something. It's very binary, so to say. The next big step forward, and the first time where this actually became airborne, was with the invention of AM radio, or radio, as it was just called, because that was the only kind of radio there were. So AM radio, the reason why it's called AM is because it stands for amplitude modulation. And the reason is that when I speak, I actually produce waves in the air. Air molecules are being pushed, and that's how you can hear me speak. In this case, it's picked up by the microphone, turned into an electric signal, which is basically also a wave, but it's moving really, really slowly. And we could technically take that wave and plug it directly into the antenna, but the issue is that we would need to have a really, really big antenna, because the slower the frequency, the larger the antenna we need. And it would be totally impractical to send and receive waves in that speed. So we need to speed it up very, very fast to get it into smaller antennas. And so the way AM goes about doing this is that you take the very slow-moving wave that you see on top, and then there is what's called a carrier wave, which is that's the frequency you're tuning to on your radio. And it takes the shape of the slow-moving wave. In this case, it could be a song you're listening to on the radio. It could be my speech. And it's changing the amplitude of the carrier wave depending on the amplitude of the slow-moving wave. And then you get AM, or amplitude modulation. So after that, frequency modulation came. It's a little bit more complicated, but it's basically the same thing. You have the slow-moving wave on top. You have the carrier in red. And then in the bottom, you have the frequency modulated wave, where the frequency basically changes depending on the incoming signal. So we've had that for a long time, and that's worked very well for our radio, AM and FM. But what about digital? So digital modulation is close to the same, but a little bit different. So what's the most simple form of digital modulation? Let's go back to our telegraph key here. If you think about it, it's basically a bunch of ones and zeros. Either the circuit is connected or it's not connected, right? It is what's called on-off keying. And that's actually what this the radio inside this car is doing. It's sending a bunch of ones and zeros using on-off keying. And that's what I've emulated or replicated with my radio here. So if the carrier wave is present, it's a 1. If the carrier wave is not present, it's a 0. So that's the most simple form of digital modulation. And in this case, 1 bit is what we call 1 symbol. And a symbol is like the atomic piece of information we are transmitting. We can only transmit 1 symbol at a time over a radio wave. So in this case, the symbol rate is equal to the bit rate. And what I wanted to find out is to speed this up, how can we maybe have more bits per symbol? Because that's what all the cool kids are doing today in radio. So in digital modulation, there's basically 3 types of modulation. And by the way, before I go any further, I know this is super theory and all that stuff. I'll get to some demos soon. And this has taken me a long time to understand. So I don't expect you to grasp it all. And you're, of course, welcome to talk to me later or ask me on Twitter or stuff like that. But just to let you know, this can get a little bit hairy. Anyways, so there is, in digital modulation, there is 3 basic types of modulation that we make use of and combine in different ways. So there's the amplitude modulation, as we saw before. We call it amplitude shift keying when we are talking digital modulation. There's frequency shift keying, which is basically the FM. And then there's another thing we haven't looked at before, which is phase shift keying, where we change, basically, we move the peak back and forth, we move the phase of the sine wave back and forth and depending on where the peak and the valley occurs, that's either a 1 or a 0 or something else. How many remember one of these? Oh, a little bit elderly audience here. So I used to go online with one of these. Actually, this is one of the older models, 56K modem. And the reason why it's called a 56K modem is because it can transmit 56,000 bits per second. But you probably, when you were using these, you probably came across another term called baud. So this was an 8,000 baud modem, which is basically means how many symbols it can send per second. So this particular modem can send 8,000 symbols per second. So there's 8,000 times a second. 8,000 times a second. It does something to the wave to change it to send a new symbol. So it basically means it can send 7 bits per symbol. So in some way, it manipulates the radio wave so it can send one piece of information, a symbol, but that symbol contains 7 bits. So that's how it gets the bandwidth up. So we're going to fast forward really far here and talk about basically the one type of digital modulation that everybody is using today. It's called QAM, or quadrature amplitude modulation. Your phone in your pocket today is using QAM. The Wi-Fi that you're connected to is using QAM. Everything today is using QAM. So to understand how QAM works, and I'm sorry, this is I'm sorry I have to do this to you. I mean, I had to read up on this as well because I did not, I was not a good student. But it's actually really simple. If we have an angle on a circle, and we take the sine value of that, that's basically the y-axis, how far up the y-axis that we are going if we have a length of 1. And the cosine is how far out the x-axis we are going. And so if you think about a sine wave is basically the y-axis, the point on the y-axis just going up and down as you have the angle going around and around and around on the circle. So that's your sine wave. And similarly, the cosine wave is the x-axis. And if you plot the two together, you have these two curves, two waves, which is about, or not about, exactly 90 degrees shifted. So the peak of one curve comes 90 degrees delayed from the peak of the other curve. And if you think about it, if you have these two waves, you can actually pinpoint any point on this circle. So you have an x and a y coordinate system. And the way that all of these software-defined, or 99% of these software-defined radios work is that they work with these numbers. We call them complex numbers. We're not going to go into that. But basically, it works with an x and a y coordinate system of these two waves. In the end, those two waves are going to be combined into one wave and being sent out over the antenna. But when we are working with it in software, we just have these two numbers that we can always manipulate. And so we always think about this thing we call the unit circle. And the unit circle is basically the distance from the origin and then one out. And that gives us a point on the unit circle, which is the cosine and the sine of the angle. And using this information, if we are clever enough about when we look at the point, because the wave are of course moving all the time, but if we agree like, okay, we are going to look 8,000 times a second, and we're going to start now, and then we're going to do dun, 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 dun. Then we can actually manipulate the wave to be at a specific point. This point, we can make sure it is in a specific place around this circle 8,000 times a second. And so we can then agree that if we find the point to be in the upper left corner, it's 2 bits, 0, 1, and then upper right corner is 2 bits, 1, 1, et cetera, et cetera. And that's just manipulating basically these two waves. Then we can get 4 points. And suddenly we managed to encode 2 bits into one symbol. But this, of course, can go up from there. So we have 16 QAM, where instead of only manipulating how it goes around, we also manipulate the amplitude, basically how much power. And then we can have 4 bits. And if we have 256 QAM, we have actually a full byte of information for each point. And then as the time moves on, we just make sure to move that point around. And as long as the sender and receiver is in agreement of when to look, and that's some of the tricky part, but there's some math on how you can agree on these things, then we can actually send bytes really, really high speed over the radio waves. So unfortunately, we're not living in a totally quiet world. There's a lot of radio waves. There is like lightning strikes. There is somebody turns on the microwave, there's a lot of radio going around, so there's going to be errors in the signal. So the next thing I needed to figure out when I was looking into this, so now I have the theory on how to pack bits really, really tightly, but I need to error correct because errors will happen. And we all, computer people, we know that, oh, if I receive a packet with TCP/IP and it's corrupted in some way, or maybe I didn't receive it, so I'm sending back a signal to the sender saying, oh, I didn't receive this package or it was corrupted, can you please send it to me again? That doesn't always work in radio. It could be that you have a sender-receiver situation where the receiver can only receive, it has no way of sending. Or it could be that the distance between the sender and receiver are so great that it's simply impractical to send a message back and saying, I want to get this data again. Like, think about how are we talking to the rovers on Mars, for example. There's a long distance. The turnaround time is too big. So people have been thinking about this, of course, since the early 1950s. And in 1949, they invented something called GOLAY codes that was actually used on the Voyager 2 probe on the Jupiter and Saturn missions in the late 70s, early 80s. And then in 1950, Hamming codes were invented, and it's actually used today in all your servers for ECC memory, and the reason why it's called ECC memory is actually because it stands for error correcting codes. And then in 54, something called Reed-Muller codes were invented that was used on the Mariner spacecraft. And in 1960, Reed-Solomon codes, which was also used on the Voyager 2 spacecraft, were invented, and it's actually also used in CDs and DVDs and Blu-rays and barcodes today. So the reason why if there was a scratch in your DVD, it's not because you have a super powerful laser that can kind of look through the scratch. It's because it's using Reed-Solomon codes to figure out what the missing bits are. It doesn't need to, you don't go back and get a new CD. You can actually figure out what the missing bits that was supposed to be there in the scratch were. And then today, everybody is using turbo codes. So your phone in your pocket, using LTE, it's using turbo codes. That's basically the new kid on the block that everybody's using today. It's used in everything from deep space satellite communication. Like today, that's the thing. The easiest thing to implement and understand is Hamming codes, but it's really not that great if you have a lot of errors in your signal. So either it's Reed-Solomon codes, turbo codes today, and luckily we have NPM, so we don't need to reinvent the wheel, so we can just do NPM install Reed-Solomon, and then we're good. So that's taken care of. And then we just need to basically put all this theory together in software, and then hopefully it will work. So I built this Electron app, and the reason why I built it in Electron, oh, wait a second. There we go. The reason why I built it in Electron and not just as a web browser was because I needed to be able, to talk to the USB. So here I'm listening on 27 megahertz. Which is the frequency that this remote is operating on. And this is a remote control for the car. Let me just make sure I switched it off. I did. So when I press forward here, we can see there is a signal at 27.144 megahertz. There's a little bit of aliasing on the other sides, but the main signal is on 27.144. So this allows me to look at the signals and do a lot of interesting stuff. It also allows me to graph what I'm sending. So basically, I have a message I want to send. In this case, it's Hello Island. I prepend a preamble to kind of let the receiver know that, oh, now the actual message is coming. I turn that into bits, and then I turn those bits into symbols. In this case, I'm using QAM 4. So the 144 bits needs to be sent in 72 symbols. And then the blue line here is actually the resulting radio wave that I'm generating. If we zoom in, there we go. Oops. There we go here. You actually see that as the bit, the symbol changes, I'm changing the phase. I'm basically shifting the way that this angle is kind of placed using this wave. So here, instead of continuing up, it's suddenly it's like it's on a different place on the circle. So I'm kind of changing the location on the circle that the point is right at when I get the new bit. And then I have the receive signal. And in this case, I've kind of cheated a little bit. So I've hard-coded kind of the amplitude where I'm kind of considering that a signal is. So I have a minimum threshold of when a signal is coming in. Normally, what you would have to do, you'd have to do some what's called auto gain control, where kind of the further away that the sender was from the receiver, the gain, of course, is like it's a fainter signal. So you have to kind of artificially compensate for that to kind of get a uniform gain across the entire radio spectrum. But I've cheated a little bit here. Then finally, I'm basically running that thing in reverse, where I kind of encoded it and getting the bits or the symbols out, and then from the symbols I get the bits. And the message I sent was "Hello Ireland," and the recovered message from the radio signal was "Hello Ireland." So it works. Some references. If you ever get a hold of one of these, and I can really recommend that, these radios here, you can use my Monster Drift application. You can do npm install Monster Drift. You can remote control any car, any toy car. And then if you want to just really get into the dirty details of how to work with this HackerF hardware with Node, there you can install the HackerF module, which gives you like raw access to sending and receiving data. And by the way, this one can send and receive on every frequency from 1 megahertz up to 6 gigahertz. So you can send FM radio if you wanted to do that. You should probably not, because that's illegal. You could unlock cars. You could do stuff. And then finally, there is greatscottgadgets.com, which is where I bought this one. That's the guy who made this. He runs the website Great Scott Gadgets. And if you go to /SDR, and that one there he's done some really, really awesome tutorials on how to understand all the math and receiving and sending signals and how radio waves work. I can really recommend that. It's super awesome, that's basically the tutorials that got me started with this. And then finally, you can tweet at me. I'll do my best to help you, and maybe we can become wiser together. And that's it. Thank you.